Well, good evening, everyone. You may see Aaron and you might see me. This is the fun part of these Zoom meetings. Um, Aaron is somewhere in the world, but his other half is with us tonight. Anyhow, welcome to BS&BEER Canada. We've got a great presentation coming up. We'll do an intro with him in a second, but first we'll do an intro with our amazing host. I'm Sean Sanamore, VP of Construction here in Vancouver. Oh, wrong side over there, and involved with many amazing things involved in building science. But this is the best part of this whole thing is teaching and educating, collaborating, sharing, and hopefully again bringing up the way that we build so that we know better and we build better. So glad to be here, and I have luckily had extras from hockey, so I'm going to have a Coors banquet. But of course, it needs to have a sweater, and so thanks to our good friends at Sashco, this cup. Oh, of course, it's a bit too. Oh, and we'll do. You know what? Sorry, we'll give some love to Zip. Gotta have sweaters, so the beer is going in a sweater, folks, just like our homes. All right, Justin, over to you.
All right, thanks, Sean. Justin with Element Construction out of Saskatchewan. Yeah, focused on high performance, new homes and renovations. And yeah, I don't know for those maybe right somewhere about there in the middle. I won't take Connor's center of Canada, but I am truly more center of Canada.
Geography, just not people and culture, hey?
That's right.
There you go. I'm Connor Bulloy. I'm a designer, builder, and educator in Toronto. I teach full-time at George Brown College. We teach a post-secondary carpentry program, really focused on building better, building science, and also building businesses. Pleasure to be here today. I'm looking forward to Grant's presentation and to continually learn. So thanks for coming, Grant.
Yeah, thanks for having me.
We're in the middle. We're down there, right? We're in the center. So
Like a test doing the where am I on the map?
it's like basically my clavicle is kind of where I'm located. So that's it. Over to you, Lori.
So I'm Lori. I don't always look like a collage, but anyway, that's what the tech is doing for us today. I live in Halifax, but I'm actually in St. John's. Wrong. See, I can do it almost. I am a designer, building science specialist, passive house designer. I was actually here for the Newfoundland and Labrador Architects Association to give them a talk today about passive house building. So, yeah, and I have been wet all day because I walked there, and I'm just because of that, I'm enjoying mint tea in my hotel room.
All right, excellent. Well, let's kick it over to Grant, who is here. So, Grant, a couple things. Today is about vapor retarders and alternatives to the famous 6 mil poly. So, we're going to dive into those fun details. But you know what? Why don't you get started and tell us a little bit who you are and how did Mr. Aaron Jones, oh, that guy, uh, connect with you to get you here today?
Yeah, thanks for having me. Really my pleasure to talk to you guys today. Let me share my screen and then we'll go from there. All right, everyone can see this? Or did it go through?
Nope, try it again.
Still see you.
Yeah, looking better.
How's that?
There we go.
Yeah, so my name is Grant. I'm a building envelope engineer, high performance building engineer, kind of guru. And I've been doing this for about 15 years or so. And I met Aaron 2 years ago at Building Science Summer Camp, actually just outside of Boston, that Joseph Stiebrecht and Building Science Corporation puts on, which is a really cool event. And you meet a lot of giants in the industry and a lot of mentors that that are there to help and eager to help. So I met him there 2 years ago, and I saw him again this past year. And this past summer, he invited me to come on to the show, and I was more than happy to oblige. So today's discussion is vapor control in cold climates. There's a lot to cover. Um, and I really like discussions if people, if they can chime in and interrupt me, I don't mind, and have this kind of discussion and not just make it too dry, because a lot of this information is pretty technical. Me being an engineer, I'm a little bit more technical focused, but I like to kind of break away from that if you know you want to chime in, and if I'm talking a little bit too ahead of myself. But I did try to make it so it's not too dumbed down. It's quite it is quite informative to most people. And vapor control, I think, is pretty interesting topic because I've been learning building sciences for over a decade, and 3 years ago or so I thought I knew quite a bit about vapor control. And then I bought Joseph, and I read Joseph Stiebrick's book called Moisture Control for Residential Buildings. And it really kind of blew me away on what was being discussed in it. So I dive into sections of that in here in this presentation. So just to kind of get a little bit of my background for everyone, I went to school as a civil engineer and graduated about 15 years ago. Worked in the construction industry for a couple of the years, and then I felt that, civil engineering, structural engineering kind of wasn't totally my path, and I wanted to get a little bit more from it. So I actually ventured across the pond to the United Kingdom, where I did a master's degree at the University of Bath in innovative structural materials. And doing that, I took an auxiliary program that they were offering for the first time ever called Passive House. And so I jumped on this Passive House course. It wasn't part of the curriculum I was doing. It was an extra. And I got really excited about what Passive House was and high performance buildings and building science. So after that, I came back to Toronto. I'm originally from Winnipeg, moved to Toronto after I did my studies. And that's where all the big buildings are. That's where things were really happening and moving. So I went to Toronto and I worked in restoration construction as an engineer, and then more into the building sciences as well. And when I was there, I designed and self-built my first deep energy retrofit project, the house that I was living in, which was a complete real disaster to live in a project for those who have done it, because your brain never turns off. And me being pretty meticulous, it took several years. It took quite a bit of years, and I did it myself, and the other person that I purchased the house with. But we did it, and we did it as per the saw cut deep energy retrofit, where you encapsulate the entire building, entire house with exterior insulation. You saw cut the overhangs. You create kind of this monopoly framing with the insulation, and then you build on and frame on your overhangs to make the architectural features thereafter. And I learned a lot doing that. It was an incredible learning experience. You deal with all these different types of materials and membranes and windows, and it's your own money and your own time. You really put a lot of thought and time into it. That took me back to Winnipeg. I moved back to Winnipeg in 2020. Had my wife and I had our first son, and we came back to be with family. And I started another deep energy retrofit, which was another 120-year-old house, applying kind of different systems but similar principles of high performance building. And then recently, last year, I launched my own company, Litebox, and we do and specialize in high performance buildings. And we really want to improve the building stock and the education of consultants and of designers and contractors. And so that's my real passion. And then I also got Fias certified this past year to be in tune of what these, high performance green certifications are all about. So that's a little bit about me. Now jumping into the presentation, there's a lot here. I'll try to cover as much as we can. Main talking points. So just going to review the 4 principal control layers, why we need vapor control and do we need it? What's a vapor barrier, a vapor retarder? Sometimes they're referred interchangeably, and what it's not. The 3 methods to control vapor. It's not just a vapor barrier, right? And we'll get into that. That's just one of the methods. What do the codes say? Both the Canadian and American codes. So the American codes are actually really updated and really advanced compared to our Canadian National Building Code. And we'll jump into that. And then lastly, if we got some time, we'll review some below grade vapor control, which can get pretty tricky. Okay, so 4 principal control layers. We have our water, air, vapor, and thermal. You probably have seen this many times in the past. They're listed in the order of importance. So water is the most important, then air, vapor, and thermal. The code and the longest sections of the code recognize the least important, which is thermal. It's all about insulation values is in the codes. And the codes say very little about water, except it can't leak, and air for it to be airtight. Vapor, there's a little bit more information on it, but not too much either. At least in our Canadian National Building Code is very little. Okay, so high level look at these each. So water control, so it's the most important because it will destroy your buildings the fastest, and it's the number one reason for complaints from the clients. Middle of the night, get a call for water, but you won't get a call for drafts or feeling a little bit chilly, right? Shingle lapping and redundancy is incredibly important, and directing water out and away, flashing. So when I looked at this, putting this presentation together, I tried to find that the Flash Me logo, and I couldn't actually find it. So we got this nice gentleman on here looking pretty good with the Flash Me logo. Air control, so its primary purpose is to keep out stuff out, in stuff in, outside stuff in. Outside stuff out and inside stuff in. Outside isn't necessarily fresh air. The outside air is getting dirty. There's bugs. There's all kinds of different things, right? When I built my first kind of high performance building and it was super airtight, my wife even said she's scared of spiders and doesn't like spiders and bugs, and she's like, we don't have any spiders or bugs, like why is that, like, well, our house doesn't have it. And it was an attribute I didn't even think that would be that you get out of having a very tight building, is very little to no bugs because they're not crawling in through cracks. Continuity is critical both for a lot of aspects: health, comfort, durability, and energy. And vapor diffusion usually never kills a building. Air leakage does. So a study by Building Science Corporation was done for the climate of Chicago, is in this example here. So they looked at 2 different systems. One is a sheet of gypsum drywall with vapor diffusion for one heating season through the winter in Chicago, which is climate zone 5, similar to Toronto, climate zone 5, versus a 1-inch square hole and having air leakage through that hole, with a pressure differential of 5 Pascal, which would be a pretty typical pressure differential you'd find. And the 1-inch hole represents about the size of an electrical receptacle. And what they found is that the amount of water that goes through that wall assembly, through that 1-inch hole, is about 100 times greater than the vapor diffusion through gypsum board. And that gypsum board does not have a vapor barrier. It's just painted drywall. So you can see that air leakage is much more important than vapor control. Okay, so vapor control is their third one. Resist phase change of water vapor to a liquid. So So air can only hold a finite amount of moisture, and that's dependent on its temperature. So inside in winter condition, we generally want to stay at around 20 degrees Celsius, maybe 30 to 40% relative humidity. As that air with that temperature and humidity moves through your building envelope, building assembly, it gets cooler. And the cooler it gets, the less it can hold. And so the relative humidity increases until it can. So if that travels through the wall, you'll get interstitial condensation, is what it's scientifically referred to as. So it's condensation with your wall assembly. So you want to prevent that from happening. Dryability is more important than wet inhibition. I came up with those words. I don't know if that's correct wording, but it sounds kind of good to me. And Joe Stiebrecht said this about vapor barriers, specifically polyethylene vapor barrier. One of the problems in the building industry is that we have a spreading cult-like mentality that worships at the church of polyethylene. This cult is responsible for many more building failures and building successes. So as we provide a barrier that stops or almost 100% stops vapor diffusion, that also stops the wall assembly from drying. So incidental moisture getting in your wall assembly prevents it from drying. So it's a double-edged sword. And lastly, thermal control. So our aim is to minimize thermal bridging in cold surfaces. And as Allison Bales kind of wrote in one of his blogs here, every object radiates heat, and the amount of radiant heat it gives off depends on its temperature, to the fourth power, which is which would have a very high effect. Also, its surface area and emissivity. So the surface of the window is much colder. So the man is giving off a lot more radiant heat and to the cold window, and therefore he feels really cold, right? So it's mean radiant temperature that drives comfort, not air temperature. Okay, air control or vapor control. So do all buildings need vapor control? Well, let's look at this example. So this is a multi-unit residential building, photo I took in Toronto. Thermal bridging is causing that concrete ceiling to be cold. And so water is condensing and black staining is occurring, or mold is occurring on that ceiling. So it's an issue with, is that a vapor control issue? Yes. Is it a thermal issue? Yes, as well. What about this one? So spalled brick on a mid-rise building. And it's protected by deep overhangs of the roof. And the lower sections don't have spalling. So why is that spalling happening? Right? You can see that that brick is spalling. So kind of some fancy wording here, names hygric buoyancy and thermal buoyancy. So what those two things are, hygric is moisture. So dry air is very dense. It settles on the lower levels, and moist air is less dense, so it rises. And then thermal buoyancy is hot air rises. So those two things kind of also referred to as stack effects. So stack effect pressures pushing through the apartment buildings into the units through the walls and wetting that brick and spalling that brick. So both a vapor and air control issue. So all buildings need vapor control, but that does not necessarily mean all buildings need vapor barriers. So quick history on vapor barriers. William Rose's book, Water in Buildings, is an excellent resource for this. The history of it, not just for the history, but it's just an excellent resource for water in general. But it really dives deep into the history of the infamous polyethylene vapor barrier. So 1930s insulation, fiberglass insulation was invented just after or during World War I, and it was implemented into houses around the 1930s. So people started insulating their cavity walls, and their cavity walls got colder, and their wood clapboard siding started the paint started to peel. And so painters actually started to refuse to paint these types of houses that were insulated, and they were erroneously blaming the insulation on drawing water into the walls, and not considering drip edge flashings or extra wetting from the exterior that was also happening. Because once you start insulating walls, you start reducing the amount of heat flow, that waste heat flow from the inside, and keeping those wall assemblies warmer and drier. So the colder they are, the wetter they are. And so that was what was happening. It was not necessarily an issue coming from the inside. And even in the 1950s, I think it's 1951, the National Paint and Varnish Association campaigns for vapor barriers to be installed in buildings. And then ASHRAE kind of took this on. It wasn't just vapor barriers that came out of it. It was ventilation for crawl spaces and roofs, and but vapor barriers also came across with it, and hence the infamous polyethylene vapor barrier kind of was born into our buildings. And the building codes haven't changed much. At least the Canadian ones haven't. The Americans has changed actually quite dramatically the past recent amount. Yeah, okay. So what's a vapor barrier? So it's a distinctive water control layer to control water vapor, and it's a vapor diffusion throttle. So it throttles vapor. That thing keeps popping up. Okay, what it's not. It's not house wrap, waterproofing membrane, or air barriers. Sometimes you'll see on site or people start talking about, oh, we got a hole, we got to patch that vapor barrier, we got to put the vapor barrier on, and they're talking about house wrap. That's not correct. They can be that. They can also double, and a vapor retarder can also double as the air barrier, and many times it is, or also the water control layer. But they are not the same. So like I was talking about before, vapor barriers can be a double-edged sword, so vapor retarders. So while they reduce the wetting potential associated with vapor pressure difference, they also reduce the drying potential. So William Rose, from the author of that book, recommends that for design purposes, we should assume that 2% of water that impinges on wall traverses the weather barrier, like gets into the wall assembly through the brick, through wood cladding, your siding, your stucco, etc. So we should design for moisture to be coming in, and we should design for that moisture to get out. So building materials can get wet as long as they don't stay wet. If they stay wet, then bad things happen, things start rotting and rusting. Okay, so three methods to control vapor. So the first and the most obvious, and everyone knows about, or probably is relatively aware of, is a vapor retarder, vapor barrier. Okay, so this is a physical layer to retard vapor flow. An example is the polyethylene vapor barrier. The second method is to actually control the condensing surface temperature. So what does that mean? If we put exterior insulation on a building, then that raises the cavity surface temperature, which doesn't allow that hot, moist air that does traverse through the envelope to ever condense. If we can keep the temperature of the sheathing above dew point, enough above dew point, then the risk of condensation or interstitial condensation reduces dramatically. So we can do that. So we control the condensing surface temperature with exterior insulation. And the third is vapor flow through assembly. Now, the vapor open through the entire assembly. So that also includes the exterior cladding. So what this typically will be is latex painted drywall, some type of fibrous insulation inside your wall cavities. You could have exterior insulation as well, as long as it's vapor open exterior insulation or semi-vapor open, and then a drained and ventilated rain screen cladding. So so the moisture load is greater or is not, the moisture load is less than the moisture dissipation. So as vapor is going and traversing through the wall, it's dissipating on the outside faster than it's accumulating. So a limitation to vapor flow through assembly is cold climates. So in our cold climates, climate zone 6 and above, and I'm in 7, Winnipeg. So vapor flow through assembly does not work here. Our winters are just too cold, so our moisture load is just too great for how fast that moisture can dissipate. And then another limitation is also reservoir claddings because of solar drive. So reservoir claddings like brick cladding, it'll get wet, rained on, and then the sun will come out and it could drive that vapor back into the assembly because it's totally vapor open. So we have to be careful with that. And there's a lot of good readings or more readings on this in Joseph Seabrick's Moisture Control for Residential Buildings. Okay, so diving a little bit into controlling the condensing surface temperature, getting a little bit nerdy here. So this is taken from Joseph Stiebrick's Moisture Control for Residential Buildings book. This graph is based on Climate Zone 5 Chicago. So the assembly is just a 2x6 wood framed assembly. So it's R19 cavity insulation filled, and you can see that in winter time, which is typically we design for a relative humidity of 35%. So at 20 degrees, which is 70 Fahrenheit, is approximately this line here. So anything below that line suggests that there is a potential for condensation to be occurring within the wall. So, and that point is right at the sheathing. So that is our condensing surface of interest. Now, if we put exterior insulation on that same assembly, well, it's not the same assembly. It's actually downgrading it to a 2x4 wall filled with cavity insulation and putting 1.5 inches or 2 inches of exterior insulation on there. What that does is it shifts that line up. So it brings it above that risk of interstitial condensation. So we're bringing it above. So that's what we want to achieve when we're using this approach for vapor control. Okay, so into the codes. First, we'll look at the Canadian codes. What does our Canadian code, National Building Code, say? So this section is pulled out of Part 9, which is the residential small housing section. And essentially what it says is there's one option to provide vapor control, and that is a vapor barrier. So vapor barrier, vapor retarder. The Canadian code uses the wording vapor barrier. The American code uses vapor retarder. Typically with the language that we use with the high performance building community is typically vapor retarder. Interesting to note, vapor barrier was actually in the ASHRAE back in the 1970s, but there was a lawsuit against them, and the lawsuit's claim was that vapor barrier suggests that it's an absolute barrier to moisture, and so they changed their wording, and that's why in the American code is purely referred to as vapor retarder. So our code requires a vapor barrier, and it requires it to be 60 nanograms per Pascal per second meter squared. Essentially, that's approximately equivalent to 1 US perm. 1 US perm is 57, so it's very, very similar using the dry cup method. And for using exterior insulation, there is kind of the sentence at the very bottom where it says, where foam plastic insulation functions as the vapor barrier, it shall be sufficiently thick as to meet the requirements of sentence 1. So it's not really saying that there's another option of controlling the condensing surface temperature. It's just saying that if the exterior insulation is also acting as a vapor barrier, it can be acceptable. So that exterior insulation, it does apply, but it only applies to foam plastics because they can become one US perm or less with a certain thickness, where mineral wool or fiber wool or any other type of fibrous exterior insulation would not satisfy that code reference. And then it also gives the option for kind of smart vapor variable retarders for foundations in this sentence. But that's as far as it kind of goes there. Part 5, which is the non-residential part, pretty much says the same thing, but it gives a little bit more acceptability to the designer. So there's no prescriptive guidelines, and this requires the designer to have a lot of input and knowledge of vapor retarders, which is not great. It's unfortunate. Okay. Now the American codes, what does the IRC and the IBC say? It actually says quite a bit. Yes. And it's a great reference too, actually. It's free. It's all online. So it's all free and you can find it too. So it's not like you need to pay a subscription to purchase it. So I do recommend that even though we're in Canada, it's still a really good reference to be using because it is far more advanced. And I think that's coming a lot from the influence of the work of Building Science Corporation, from my understanding. Okay, so there's section for vapor retarders. Again, it refers to them as vapor retarders and not barriers. Okay, so vapor retarder says buildings need vapor retarders. Should be provided on the interior side of the frame and in compliance with a couple tables there. There's exceptions, basement walls, and below grade portions of any wall. And then there's also an acceptable in table 5 of this section. So it's interesting that it says basement walls and below grade portions of any wall are not. It doesn't say that they don't need a vapor retarder, but the section just excludes them. So that was kind of interesting to see. There's 3 classes of vapor retarders. So they have 1, 2, and 3 class. So the first class is the perm rating of less than 0.1. So 0.1 perm, so that is a pretty impermeable membrane. That would be equivalent to our standard polyethylene vapor barrier or foil-faced rigid insulation board. Class 2 is our closed cell spray foams, our perforated foil-faced EPS boards, XPS, and vapor retardant paint. And then class 3 is pretty much latex painted drywall. And that's a perm rating of between 1 and 10. So the vapor retarder options, it's this last section down here for all of Canada, because from Canada is Marine 4 in Vancouver, and then all the way through the provinces up to and territories up to climate zone 8. So class 1, so vapor impermeable is permitted, and there's a couple notes there, B and C. The other sections, it's also permitted for class 2, and then class 3, it says see this table, which we'll take a look at, and that table is pretty much talking about controlling the condensing surface. Okay, so down here, B and C, what is that saying? So B and C says this. So framed walls, the use of a vapor retarder that is not a responsive vapor retarder on the interior side with a class 1 vapor retarder on the exterior side shall require an approved design. Okay, so what is a responsive vapor retarder? This is new definition that's just been updated in their code. So if you haven't looked at their code in the past couple months or so, this is brand new to a brand new definition that they've included. So this is a smart vapor retarder, but they're referring to this as a responsive vapor retarder. So it's a material complying with a vapor retarder class 1 or 2, but it also has a vapor permeance of 1 or greater for the wet cup method, which is procedure B. Okay, so both these B and C both indicate not allowing vapor sandwiches, which is really great to see. Vapor sandwiches is where you completely trap in your wall assembly, in your cavity wall assembly by two impermeable or near impermeable, vapor impermeable membranes. Okay, this table 3, this is for controlling the condensing surface temperature. So this is where I think it gets pretty neat, where it dictates where you need to be, and it prescribes and provides a little bit more information and guidance to a designer when you're looking at, okay, if I don't want a vapor barrier, if I don't want a vapor retarder on the inside, what would I need for exterior insulation? Then I get rid of that poly vapor barrier. So, well, let's back up here. So Marine 4, again, that's Vancouver, 5, 6, 7, 8. So 5, Toronto, and 7 would be like Winnipeg. So take Winnipeg. So if we have 2x4 walls down here, we need exterior insulation, continuous insulation on the exterior of R10 or greater, as an example. And if you do a 2x6 wall, then it'd be R15 or greater. It also talks about vapor flow-through assemblies. It doesn't label them as such, but it is showing that. So it's showing these vented cladding systems. So this is with class 3 vapor retarder on the inside, which means painted drywall. And it's therefore vapor open. So if you also have a vapor open exterior cladding, then that satisfies your vapor control requirement, which I think is pretty neat to see how to see that. Yeah, down there with rain screens. So vented cladding means rain screens. Okay, so, and then there's also, if you are going to provide a class 1 or a class 2 vapor retarder, you can also provide exterior insulation, and kind of dictates what's required there. And the values are less. So they're about cut in half. So again, climate zone 7, if we're looking at Winnipeg for a 2x4, it'd be 5, R5, where if it's just a class 3, it's R10. So it's less exterior insulation that you require. But again, the previous note says that you can't create a vapor sandwich. So you have to be careful, because exterior insulations can very well, if it's a foil-faced exterior insulation is a vapor barrier. So you'd create a vapor sandwich with this system with interior class 1 or class 2. So these values are presumed to be based on normal interior conditions. So that means wintertime maximum 35% relative humidity, and you'd have to increase your continuous insulation by 1.5 times for every increase of 15% RH. So why would you have to do that? Is if you have buildings that are wetter. So if you have like if you have a pool room, for instance, in a building, so those temperatures and relative humidities are going to be much greater, and so therefore you would have to increase that amount of exterior insulation much more. There's another table on having absolutely no vapor retarder either, neither a class 1, 2, or 3. So essentially that means kind of just open wall assembly. That's brand new, because that's shown in blue. So that's brand new change to their code. And I'm not sure kind of an example of what that would be, but I imagine, I guess, that there is, and that's why they provided that. And then there's also the option for closed cell spray foam and what that would look like. And again, using the building science to determine what that looks like. So lots of guidance on on that. And then for unvented attics, it also has a good blurb on here as well. It needs to meet all these parameters. So interesting to know that for a vented attic, or an unvented attic, so no vapor barrier is allowed on the ceiling at all. No open cell spray foam for climate zones 5, 6, 7, and 8. And pretty much to comply with these insulation amounts for again, controlling the condensing surface. Okay, this last section here talks about, it says alternatively, sufficient rigid board or sheet insulation shall be installed directly above the structural sheathing to maintain the monthly average temperature of the underside of the structural sheathing above 7 degrees Celsius. For calculation purposes, an interior temperature of 20 degrees Celsius is assumed. So why roof sheathing above 7 degrees Celsius? So getting a little bit nerdy into understanding that, we can look at the psychometric chart here. So, okay. So psychometric chart, if you're not familiar with it, we have temperature on the bottom, we have relative humidity at the top here, and these are kind of on a these are angles. So 60% here is you follow that line down, and then on the vertical axis, that's your vapor pressure. So for 7 degrees, so at a dew point at 20 degrees Celsius interior temperature at 35% relative humidity. Okay, so 35% is between 30 and 40%. So we follow this line down and we hit approximately here because this is our 20 degrees Celsius. So that's where our line is. So what would that look like if we went over and hit dew point, which is 100% relative humidity. So you follow the last line here is 100%. And where does that hit? That hits around 4 degrees Celsius. Okay, so we're at 4 degrees Celsius, so that doesn't understand why we need to have our roof sheathing at 7 degrees, though, above 7 degrees. And the reason being is because in porous surfaces, there's something called capillary condensation, and that doesn't occur at 100% relative humidity. That occurs actually around 80% relative humidity. So we have to kind of go back to our 80%. And so if you follow that line over, our 80% is approximately here, which aligns to 7 degrees Celsius. And so that's why, and that's what we're doing, we're controlling the condensing surface for roofs or walls. We're keeping that roof sheathing above much farther above dew point. So it's got to be less than 80% relative humidity. Okay. Okay, and then last thing about the unvented attics, which doesn't pertain to us in Canada because this is climate zones 1, 2, and 3, but it talks about vapor diffusion ports and the acceptability for using vapor diffusion ports. So I just wanted to highlight this so you understood that because you might have heard about vapor diffusion ports, and there's research even going on for vapor diffusion ports in colder climates. Not quite Winnipeg cold, but in climate zone 4 and 5. So maybe the codes will change towards that, but right now it's limited to zones 1, 2, and 3. But it's good to understand that there is discussion about what vapor diffusion ports are and their acceptability in the American code. Okay, now summing all that up, so if we took that information that the Americans have graciously provided in their building code and applied it to ours and kind of simplified it in a chart for us. So I put this together and did a quick little article on Green Building Advisor. So if you want to head over there after, and you can take a look at this table here. But essentially, I've Canadianized the controlling the condensing surface system for us. So the climate zone is the first column. Then you have the representative city, and so if we take an example, Winnipeg, which is climate zone 7A, and if we have an interior wall cavity insulation of say 2x4, we would need R10 exterior insulation to satisfy vapor control, or if we did a 2x6, it'd be R15. So it's around 2 or 3 inches of exterior insulation, which is pretty reasonable actually. We should all be kind of building to that standard already. And so what that ratio becomes is approximate is 45%. The first number is if you do latex paint class 3 vapor retarder. And the second number that's in brackets, that's if you That's if you provide a class 2 vapor retarder. So you can drop it down a little bit. But this is the percentage of exterior insulation to all complete insulation of your assembly. So 45%. I heard when I was working in Toronto, I heard kind of rule of thumb, 1/3, 2/3 for exterior insulation. And for Toronto climate, that would actually be it's pretty much right there. So that 1/3, 2/3 would work. Now, just a side note on that, and I guess I didn't bring this up initially, but so if you delete your traditional polyethylene vapor barrier, you could also be deleting your air barrier, because in many residential construction in Canada, where they use the poly vapor barrier, they also depend on that, and they are installing that as your air barrier. So you got to be careful with that. You still have to provide an air barrier, and it needs to be continuous. So if you don't do an interior vapor retarder system, and you're using this exterior insulation approach, controlling the condensing surface temperature, you still need to provide air control, continuous air control by another method. So that might still mean it's just as easy to provide a smart vapor retarder on the interior to satisfy that at the same time. Okay, so Winnipeg, yeah, that column 45% was for walls, and then for roofs, it's 60%, and that was calculated based on that 7 degrees Celsius sheathing temperature that you require. Okay, an example for climate zone 7 in Winnipeg. We got two here, so two different methods. So the first method on the left, so this is where we're using the traditional polyethylene vapor retarder, or another type of vapor retarder sheet applied behind the drywall, and that's tied into your window system. Or alternatively, we delete that, and you're relying on the exterior insulation. So a caveat to this is that you have to be mindful of thermal bridges. So if we have a massive thermal bridge going through there, then the backside of that sheathing, or the temperature of the sheathing, if your thermal bridge cuts right through, will be near the exterior temperature, and it's totally bypassing that insulation to control the condensing surface. So you got to be really careful even with detailing. So that might mean that you still need a traditional type of sheet vapor retarder to control that. Okay, doing pretty decent for time. This is my last kind of slide discussions. So vapor control below grade. So this can be tricky. This can be tricky, and why? Okay, so vapor flow goes from high pressure to low pressure, and our soil needs to be assumed to be close to or at 100% relative humidity at all times. So that's also why we have a total complete vapor barrier underneath our slabs, because the ground underneath there is 100% saturated. But on our walls, our below grade walls, our foundation walls, the soil is close to that. So vapor flow is inherently impelled to go towards the interior side most of the time. And unlike low slope roofs that see solar heat and summers with greater vapor pressures to dissipate that moisture, there is really no self-drying mechanism for foundations, because like once it's in there, it's like in the ground, right? I mean, ground moisture levels can change, and we try to keep them as dry as possible and use drainage mats, etc. But the vapor pressures are still high below there. So we take a closer look. We'll look at the psychrometric chart here, to put that into to put into a visual context here. So soil is close to 100% RH, so it's running along this line up here, and our interior temperatures are typically hovering around the 20 degrees Celsius mark, and basements range between what did I put here? Between the 20 and the 40%, right? We got hygric buoyancy. So generally basements are drier, especially this is like wintertime conditions that I'm stressing here. So somewhere between the 20 and 40% mark. So our vapor pressures are somewhere around here. Now we shift that line over. What that translates to is soil temperatures ranging between -4 and 7 degrees Celsius. So that suggests that our vapor pressures are usually much higher throughout the year, which means our vapor retarder is on the wrong side. If we're putting a polyethylene vapor barrier below grade on our basement walls, we're kind of trapping that. How this gets dealt with is through damp-proofing, actually, because our damp-proofing membrane or waterproofing membrane, but at code minimum damp-proofing on our foundation walls takes care of this. But we're then kind of creating that vapor sandwich. So there's a lot of discussions more about this in a great book called The Manual of Below Grade Waterproofing. And so, you can dive in there for more readings on this. So lastly, this is the last slide and a couple of photos here. This is a photo that a colleague sent me of some work he was done in his basement, and I actually pointed out, well, you're actually creating a vapor sandwich, aren't you? So this is below grade. This is foundation wall. So you can see silver board with it's an EPS board with a foil faced with a foil facer on there, which means it's a complete vapor barrier. And then he's putting his code mandated vapor barrier polyethylene over top of the studs. And then to make this worse is actually, this is in a shower room. So incidental moisture that gets in there from the shower could have some real detrimental effects if water got in there, moisture got in there, do a lot of damage. Especially, it looks like these are kind of like shower nooks or something that he's building into the wall. So there's high risk of issues there. So it's mindful for below grade systems on how to deal with vapor control. You generally want to insulate on the outside and waterproof on the outside of your foundation wall. That's definitely the most robust system for below grade systems. And if you can't, then you're putting continuous insulation up against that foundation wall. So that can be your vapor control, and not put a vapor barrier at all on your interior studs. So main takeaways here. So control layers, right? We got our water, air, vapor, and thermal, and the importance is in that order. Oh, not these points are in the order. Vapor control. So we have our vapor barrier, vapor retarder, our control the condensing surface, and we can do the flow through assembly. But the flow through assembly is pretty much limited to climate zone 5 on walls and climate zone 3 for the roofs. Every building needs vapor control, but that doesn't necessarily mean a vapor barrier. Simplifying building and construction with smart vapor control and smart vapor retarders. Those can be very efficient. And then the two codes. So the Canadian code is the code. In Canada we need to abide by, but it's really beneficial to look at how the Americans might be wording their codes for design guidance. But we still need to abide by our own national building code. And to satisfy authorities having jurisdiction, a building engineer could provide engineering judgments to get around the requirements under the Part 9 of the requirements of a vapor barrier. So we're not trapped. We have solutions to get out of it, but ultimately the authorities having jurisdiction will always have the final say. And that's all I got. I didn't hear any questions come through.
No, they're great stuff. There's a bunch that we'll get to in a moment here. We'll let the kind of host chat in on that. First off, You know what? I always appreciated when we got into the BS and beer, how the OGs had a book club, and every month they tried like get us started on books. You've given us three or four great books. So if they're not on your shelf, one, why not? And you've got some kind of Christmas shopping for yourselves, maybe some Black Friday deals here for yourself to make sure your
Yeah.
collection is up to speed there. Great resources, Grant. So yeah, there's three questions we'll get to in a bit here, but. Love the history lesson, love the slide deck, and I appreciate how you're definitely poking the Canadian code to say, hey, let's get into this. And I mean, it's interesting because I've seen Graham Finch from RDH discuss a lot of what you indicated with the slide decks being here in BC with our BC Energy Step Code and making sure builders we're not getting into those sandwiches that you quite eloquently discussed here. But before we get into those questions, Peter was just throwing wisecracks because that's what he does. We appreciate you, Peter, showing up every week, but we'll put you down on the list. Jeremiah and Joy, we'll get to those questions in a second. But panelists, hosts, any comments? Connor, I see you're unmuted. Is that ready? You're ready to fire away at a comment or two?
Yeah, sure. Yeah, great. That's wicked. Thanks for sharing that. I think it's, as an educator, it's always a tough topic to explain to students. Vapor is not something we can see, and the effects of, damage in our assemblies is not seen for years. So renovators definitely see what happens in assemblies. I have a question that I'm asked a lot by builders in Toronto, and maybe you can help us explain this against your presentation. When builders are moving towards recommended exterior insulation values, so let's say we have an assembly that's 30% exterior insulation. Assembly you see in Toronto right now is a 2x6 assembly with zip R9 on the outside. So you have an inch and a half of polyiso with their zip sheathing. Let's assume the building's airtight and well flashed. They put some kind of fluffy stuff in that 2x6 cavity, whether that's rock wool or fiberglass. Because they've hit those insulation values on the exterior, should and are they required to still put a vapor control or vapor retarder on the inside face of that stud?
So they don't need it for the building sciences,
Yeah,
right? But they might need it for the authorities having jurisdiction.
right.
So the cost savings, you probably, depending on the size of the project, there will probably be cost savings even if you need to get an engineering judgment letter
Mhm.
for a building science engineer to write one, review the case and write one for you.
Yeah.
But that doesn't necessarily mean that you'll get your way, right? So the engineer just provides their recommendations, and it's ultimately still up to the authority having jurisdiction on if they accept that or not. But yeah, based on the building sciences, you don't need it. Caveat to that is, though, I talked a little bit about like thermal bridging and like the effects of the thermal bridging. So it depends on like how that's being dealt with and how thermal bridge free that assembly would be. Yeah, it depends. So yeah, it really, because it's not just about like right, like how are you fastening that insulation back with strapping, or is it Z-girts, right? Like that's not even thermally broken at all.
That's,
Um,
that's exactly it, right? Like someone reads the table, they read information, they listen to your presentation, and then they ask you the simple question, say, do I need it? You're like, give me 2 hours. Tell me exactly your whole building's built. And you're right, it depends. So thank
yeah,
you.
yeah, yeah.
No, Connor, that is a fantastic question. And again, Mark, who is our foreign correspondent who can't be here today, provide us with these lovely new stickers from Offsite Dirt where we can pull up when it's like, oh, that's a it depends question. And Grant, no, I mean it's so true of you get in these complex conversations pretty quick, right? And it's like, okay, well here's your wall assembly, and then it's like, yeah, but have you done this? And you've done this, and do you have a thermal bridge? And then do you have this? And then quite quickly, it's like, well, in your climate zone, which also is a big factor there, and Connor, point out of what's happening in Toronto, of just, how we need to be just again, be ensure that your insulation, yes, might have a vapor control, or be a vapor retarder. You understand how that assembly is put together and how each material can affect that assembly. So great
Yeah.
stuff.
And even like interior conditions too, right? Like is this a seniors complex that's being built? right? Like that likely will have higher humidities, and maybe they'll be running humidifiers and have a bunch of plants. And so, yeah, it depends.
Yeah, I
I'm
think the last.
I'm gonna jump in and be a little bit argumentative on that because our passive house training and all of anybody who has sat through a lot of those Graham Finch presentations, you will know that you can have as many air barriers as you feel like, but you should only ever have one you know element that is inhibiting vapor in that assembly. And so if you know that your foam-based insulation is at a thickness that it is going to be a vapor work, functionally a vapor barrier, you really should fight to not have another one.
Hmm. Yeah, totally. Yeah, we see with like eaves cladding too, right? So like eaves
Yeah.
cladding is coming on board. A lot of builders are using it, but the poly vapor barrier is still on the inside. And then eaves,
Disastrous.
right? Eaves with that acrylic vapor impermeable kind of coating is pretty disastrous when moisture gets in.
Maybe I can question all of you all. So the OBC changed for us in 2024. There's now there is an item under vapor diffusion to talk about the allowance for, I think they call them variable permeability membranes.
Yeah.
In addition to that, and I think that's allowing builders to say, okay, I can now find a reference in the code that allows me to use a product like Intello or like Myrex without having to go and get a letter or get, testing documentation from these manufacturers. Do you think this is making it easier for these builders to use products like this in case, as already the story said,
Well, those smart vapor retarders, so the requirements for the building code is based on the dry cup method, less than 1 US perm, or close to it's 60 nanograms. But yeah, it's about less than 1 US perm. So almost every smart vapor retarder that I've come across it is less than 1 perm under dry cup testing.
hmm,
Yeah, there's a couple by Rothoblast in the early days when they were venturing over here and not having their testing yet that I actually had to provide an engineering judgment letter because they were using it in Ontario. And the authority having jurisdiction was good with that letter, but it was quite a bit of like, yeah, there's quite a bit of calculations I had to look at to see like their European testing and how the equivalent it was to the the ASTM E96 test.
yeah.
Yeah, anytime that you've got to like dive into the dry bulb, wet bulb calculation of the German or European testing versus Canadian, like have fun with that, Grant. Yeah.
Yeah, it's not too bad though.
Well, hey, well, let's just pause for a second because we're at the top of the hour. So I do get that if some people need to leave, but we've got Grant until we get through these questions. So hopefully your beverage of choice is still full, or if you need a refill, go get it. But we had a couple questions. The chat has kind of added on a few things. Glad that our forward correspondent has participated and has said hello. Sorry, has said hello. Too many tongue twisters with their vapor retarders, vapor barrier conversations. But no, Lori and Connor, great points there. Justin, did you want to chime in before we went to questions, or are you ready to get into questions?
I just appreciated some of the like below grade stuff. We struggle, like obviously in Saskatchewan, we struggle with that. We still have some authorities not really understanding that and requiring some vapor barriers in our basements. And obviously we've kind of like snuck our way in there saying, hey, this is the design we're going with. And we kind of haven't brought it to their attention. Nobody said anything, and it's worked really well for us. But yeah, there needs to be some better understanding with the authorities on having that vapor barrier in the basements. I mean, we've had it and we've seen it where we get massive ice buildups and meltouts, and because of that, right? So yeah.
Yeah, I'm surprised we actually haven't seen more failures in basements, but I think it's because the foundations are typically concrete and they can buffer a lot of that moisture too.
Right.
So because the sciences show like it's for many months of the year, your vapor pressures is on the wrong side.
Yeah, I think we've just naturally, I think some of those basements are maybe some of the folks like they have stuff up against exterior walls and the carpet's absorbing moisture and they're just not really seeing, all of the effects of that, or it's so minimal that they're not really seeing it. Whereas we've just had some experiences, especially depending on the season that the basements are closed in, that you actually have like a substantial challenge. But yeah, we've gone away from that detail about 4 or 5 years ago now, because we were just like, hey, like we worked on projects where we were seeing that. We actually had one project where we were trying to, self-diagnose and understand, hey, what happened, because we did have a bit of a buildup like that, and we went to, nope, you know what, we're 100% insulation vapor barrier on the face of the concrete. We're stacking in some rock wool on the inside just to top up our values, and no vapor barrier, short of, we actually flash it with 2 inches of spray foam right on that face of that wall to address that. So
Makes sense.
Yeah, Grant, I mean, we could spend, I mean, I think we have, whole discussion on basements because, nowadays, like even us, we've upgraded our poly product on our basements, just dealing with radon. And we're not even a radon area in Vancouver. We're just concerned about not having a robust product. And so in our basements now, on our slabs, we've gone from 16 to 15 mil product just because we just want to, belts and suspenders approach. So it's interesting just in those kind of conversations. So glad you got to bring it up. Even for us, we're an ICF builder because just being able to provide that level of efficiency, we deal with that. So great stuff, everyone. Let's get into questions because I can see there's more chatter here than I thought. And we could be here for a few hours, but let's get into at least a few of those questions before we kind of wrap things up for the night. So Al, you had a couple points in the chat. If you want to ask one, maybe I'll give you two questions, but go ahead. Grant is waiting for you there. So if you want to unmute, go ahead, Al.
Sure, yeah. Hi, guys. Yeah, well, I'm in Saskatoon, so almost as cold as Winnipeg.
You're
So
colder.
yeah, colder today probably, and we got a big blast of winter there on the weekend. But so the thing that I noticed, especially about the basements, so we just bought this 1980s house, turn of the building code, changed over from 79 to 1980. About half the house has got 4 mil poly, the other half's got 6. So it's a bit of a mishmash. But the foundation part, so I know even in the summer, and we don't have mechanical ventilation yet, but even in the summer, it was difficult to get the RH down below 50 in this house. So that's telling me, and I know where the moisture is coming from. Like it's got to be coming from the basement. It's not coming from above ground, right? So there's no, there's a weeping towel system here that drains to the sewer, no sump pit. I've never seen water coming through it, but it's got to be coming up, through the foundation walls. Like dam proofing, my dad used to do concrete work starting back in the 70s, and I worked for him. And dam proofing was, tar on the outside of the foundation wall. Most of it's spray applied now to whatever thickness, and you backfill it, and it gets scarred with dirt and rocks and everything else. And yeah, who knows how good it is. So I think a lot more research has got to happen, I think, around what do we do in the basements.
Well, it sounds like maybe your weeping tile system isn't working. Maybe you're getting a lot of moisture coming from the slab, through the
Well,
slab.
yeah, I've got a couple places where I can see I'll see a little effervescence coming up here and there. So I'm pretty sure there's, if there was, I doubt there's poly underneath the slab because back in those days, I don't think anybody did that. So yeah, it's probably plugged full of dirt, tree roots, whatever. Because when I was doing basements with my dad, we never put fabric over top of weeping tile, perforated weeping tile, right? You threw the crushed rock over top. Thanks very much. And 20 years later, it's plugged full of dirt, right? So, but yeah, so I think nowadays it's probably better. I see people doing a little bit better job of the damp proofing. Some are using the dimpled board on some of them and stuff. So, but
Yeah, on foundation walls. Yeah.
yeah, on the foundation wall. So yeah. Anyway, that's kind of my experience from here. Anyway.
Awesome, Al. Thanks for chiming in. We'll come back to that because there's some follow-up points I'll come back to. But Jeremiah, you're next. Is he still with us? There he is. Hey, you.
There we go. Can you hear me?
Mm-hmm.
Awesome. That was a great presentation, Grant. Thanks very much. That was super interesting. I had to screenshot a couple of those slides for future reference. But my question is regarding double wall assemblies in particular. I'm a big fan of double walls. I really like a lot of the aspects that system offers, especially on the exterior when it comes to detailing, claddings and things like that. Exterior insulation, I think, has a ton of value, and obviously from a building science standpoint is, probably the number one system. However, there are challenges as you go further outboard and you're detailing around windows and stuff. So I do like the double wall a lot, but I'm curious about placement of a vapor control layer on a double wall. I like having a service cavity inside so that the vapor control layer is uninterrupted and essentially monolithic around the exterior or the interior of the wall, but also like being able to insulate a little bit in front of that, and wondering what that typical ratio is supposed to be. For some reason, about 35% of the insulation outboard of the vapor control is sticks out in my head, or at least 35%. Am I sort of on the right path with
So
that?
so you could use the same ratios as that table for
Okay.
the controlling the condensing surface with where you're placing your vapor control membrane,
Hmm. Okay.
your vapor retarder in your wall. Yeah, so if you want to have a service cavity, 2x4 service cavity, and fill that with 3.5 inches of whatever fibrous insulation that you want to provide. Yeah, that would be
And
my
then
suggestion. Yeah.
looking at least the 35% kind of range beyond that, which we would normally, that would be standard anyways. We wouldn't be it'd be a fairly thick wall outside of that, but that system's worked well for us. I was just curious to know that I was on the right track kind of with the design element of that.
Well, where are you getting your 35% number from?
Well, that was a bit of searching around, like a bit of searching around on between Green Building Advisor and Building Science Corp, trying to find information on that ratio.
Okay.
I haven't found anything super helpful in the OBC charts to really suggest what that needs to be. I've also never had any issues dealing with building departments or on the design end of anything when we worked on these projects, when we've had, a 2x6 or 2x8 wall, with a vapor control on the interior of that, and then a 2x4 service cavity on the inside. I'm just more curious to know that if there was a number, what that was, and sort of what just going forward.
Yeah, I would suggest this starting with the numbers for the controlling the condensing surface surface
Hmm.
temperature table for exterior insulation, because it'd be very similar to that. That'd be the
Yeah,
starting point. So like you're in Ontario, but where in Ontario are you?
Southern Ontario, so on Lake
Okay.
Huron, down just
Okay.
north of London. Yeah,
Yeah, okay. So you're probably climate zone 6 or 5 even.
it's probably hovering right in the middle of that
Yeah.
somewhere.
Yeah. Yeah, I think you're on the right track. I think for
Yeah,
what it was at Toronto was 30, for climate zone 5 is something like 30%, I believe.
yeah, yeah. Good, appreciate that.
Yeah, no problem.
Thank you.
It's funny, Jeremiah, we just kind of default to like that 1/3, 2/3 ratio, right? Are we going
Yeah,
33%? We're gonna go 30%, we go 35%,
yeah.
where
Or
do we
does
need
it
to be?
Yeah, exactly. Or do you go beyond that anyway, so that you're on the safe side of things? Or like, where I just more curious to know. I like to sometimes know where the lower limits on these things are. Not that,
Yeah.
because there are times when you kind of need to aim down just a little bit to make something work, and you want to make sure you're not aiming too low and getting kind of below some of those thresholds in any particular situation. So just kind of curious.
Yeah, and then there's also like the risk management too, is like replacing that vapor retarder with, again, a smart vapor barrier. And like, okay, well,
Yeah,
even if it's at the 1/3, 2/3 ratio, you know that material is going to be helping you out versus
that's right.
causing grief. And it's like, okay, well, does the budget allow for the risk management of that smart material versus typical poly. So
Well,
that's
yeah,
good.
yeah,
That's
Polly's
good for you.
yeah, Polly's been out of our toolbox for quite a few years, and it's staying that way. It's not only does it pose all kinds of challenges for inward drying and all kinds of things like that, it's not really great to work with, and it's just I wouldn't count on it being a good air barrier either in that case in terms of detailing the connections effectively.
Yeah, it's funny about those typical products we've been using for years, and now we still buy them, but they're not used for the same application. They're like,
Yeah,
oh, we need to poly off a window because the window hasn't arrived yet, so we'll
yeah,
use
it works
that.
great.
But when we actually get the window in, it comes out.
Yeah,
It's actually there's a
sacrificial.
project. Yeah, in Vancouver right now, there's a really cool project called Vienna House using mass timber and prefab panels, and all the panels show up with, a high performing WRB air barrier, and yet they had to use Tyvek to close up the windows. And I was like, I
Yeah.
took a photo and sent it to the supplier and manufacturer. Was like, things have changed when
Well,
this is.
yeah, there's a reason it's on production build sites. It's very cheap, and so it can be, sufficient for sacrificial purposes at times too.
Yeah, no, absolutely. Great to see you. Thanks for joining us tonight. We are going to
Thanks.
go to Joey. If Joey's still with us, Joey, I still see you here. If you want to unmute, go ahead and ask your question.
Yeah, no, great presentation. I'm just a couple hours northwest of Winnipeg, so it's nice to, have a little Manitoba person on, and we're in that plus 40 to minus 40 area of the world, so lots of challenges. But no, my question just was in regards with ICF. It's sort of does it kind of check all the boxes as far, or a good chunk of the boxes, with foundations as far as our vapor control, things like that?
Generally, yes. Yeah, because I don't even think the ICF manufacturer instructions even require any other type of vapor control, right? I think
R-
you're placing your drywall directly on the ICF on the inside, and the outside you're putting a damp proofing membrane on of some sort, right? On the outside.
e- yeah, that's how in our area it always is done. So I guess, and my other question would be if there's any flaws in that, entire system as far as a foundation goes.
Um, no, I don't think so. The only one caveat to ICFs that ICF systems that I've come across is that if you get honeycomb, I've had a project where they got honeycombing in the ICF, and then they had a problem with mice, and they couldn't figure out where the mice were coming in. Because how do you chase that? You got honeycombing all through your ICF. So that was a really interesting point that someone had brought up. And so it's not just like structurally, if you get some honeycombing, that's an issue or whatever, but to actually start getting rodents and things like that through your ICF. So that's all I really have to say about that. But I mean, it's a robust system. It's concrete with insulation on both sides.
Okay, no, that sounds good.
All right, Joey, thanks. Finley, you had an earlier question.
Hi Grant, thanks a lot for the presentation. I was just wondering how HRVs kind of come into effect when in like vapor control.
Well, high performance building, you always want to have very airtight. So HRVs and ERVs come into play quite a bit. And typically you're looking for ERVs, unless you have a very humid building. But typically you're looking at ERVs because ERVs in summertime, you're not bringing in that humid moisture. And then in wintertime, you're not over drying your walls because you need a reasonable amount of ventilation that's going through your ERV. So does that kind of answer what you're looking for?
Yeah, for sure. Thanks a lot.
No problem.
Yeah, Grant, it's funny. I think I only live in the only climate zone in Canada where HRVs are get away with. Everyone else is like all ERVs. Actually, I think we recently just stalled an ERV only because our local supplier ran out of stock the HRV, and he's like, Sean, I know we need to meet your deadline. Will the ERV work? I'm like, yeah, whatever. Good enough. Let's move on.
Are
But
these
typically,
are they switchable cores?
yeah, yeah.
Oh,
Yeah,
okay.
no, we
So you
we
can
we
switch the
we did the
core.
whole thing and reviewed it all, but it was just funny when like the box showed up and it said ERV, and I was like, I think you got the wrong product. He's like, no, Sean, that's all we had in stock today. I was like, oh, okay, fine, here we
Was it a
go.
Zender?
No, 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 no,
Okay.
no, no, definitely not.
Okay.
Um,
Because I had
but no,
I got a Zender and it was wrong. I had ordered an
oh,
ERV and I got an HRV, but luckily they can just send me the other core, so now I have two
yeah,
cores.
yeah, I know. We don't live in the fun, humid climates of you guys in the rest of Canada. Um, Code had a question, and then I just see a whole bunch of different banters going back and forth. So, let me check on the chat. But Code, if you want to ask your question, otherwise I can ask it for you. Code's question was, oh yeah, just again, do we use wood foundations not only just in Saskatchewan but across Canada? And the only reason I thought it was a good question is recently on the Passos Accelerator we had discussions of wood foundations, and I mean they're common, like they can be used in Canada. Um, and of course, then it comes down to the same kind of details of if you're going to do a wood foundation, then you need to make sure you're doing, the right exterior work of damp proofing, waterproofing, dimple board or sorry, dimple mat type stuff. So, again, whatever foundation you do use, you need to make sure the water is staying
Yeah.
away, even below.
Doesn't PWF foundations require polyethylene, polyethylene on the outside to also protect the PWF plywood? I'm
Yes,
not
they do.
sure.
Yes, they do. I built one in
Okay.
1988.
Yeah, I
Yeah.
was gonna say, Ali, it's probably well. I know that you can do a spray applied product and do dimple mat, and the fact like the dimple mat is kind of like your rain screen, and then the waterproofing product spray applied acts as the poly. So again, it's the lovely it depends conversation of how do we manage it, what products we use, but the principles that you've discussed, Grant, is what products you're using and where's your vapor control layer, and what's the material needing to be used.
Yeah.
Yeah. Yeah. And with PWF foundations, I'll say that you should not be using poly vapor barrier on the interior. Try to go with the smart vapor variable systems.
Yeah.
Yeah. Yeah. There's in
I'm
Saskatchewan here, they've got a pretty good. We build a lot here in Saskatchewan. So both houses that we built had PWF foundations. It's just the how do you control the water? The water table I think it's a little bit archaic the way we do it here. Spec it still. I think it's still basically your wall sitting on top of compacted gravel. Um, Another house that I built had to be on a raft foundation because it was out near the river. So it had to all get bolted down. So we needed a structural engineer to take a look at it and do the detailing and stuff for it. But yeah, at the end of the day, it's just getting, having good fill around it, protecting the barrier, that water barrier on the outside. So we covered it with 1-inch styrofoam, which helped because you're going to get rocks and tree roots, whatever, poking holes and stuff. So yeah, turned out good though.
Yeah, it gets interesting again, of looking even now, we talked about the carbon footprint of just even basements. Like, okay, should we building basements or not? And then I talked to Justin about, yeah, we don't want to build basins, but when you've got your footings that have to get below the frost line and all of a sudden 4 or 5 feet down, guess what? Your clients may not want a basement, but they got a crawl space. And how do we manage, that kind of stuff? So it's always interesting about these debates of crawl spaces, basements, do we build them or not? And then end of the day, Grant, kind of as you discussed today, Mother Nature wins. She tells us how we need to build for the elements in the climate zones.
Yeah, insurance is playing a bit of a role now with basements or not, right? I've read an really interesting article a couple weeks ago about basements and premiums to insure that building, even if you're not in a floodplain or a flood prone area, like basements can add a lot of premium to your insurance. So, because then that also means your electrical is in your basement and all that other stuff. So if your basement floods, like it's a crazy amount of damage. climate resiliency, right?
Yeah. Yep. Yep. It comes back to another keyword we keep talking about nowadays. Well, I think that's all the questions. I know Code had a question about how do you know where there's honeycombing in the ICF, and I guess as you experience, because the rats or the mice came in, they found a path from the outside in, and normally that concrete would be it'd be continuous, and be all there. Oh, hey, look at that. Our foreign correspondent has a question. Mr. Mark Willie, what do you got?
Hey, Grant. Sorry, my camera's off. This is a thrilling discussion. A little sidebar. I think our storage facility, those sort of companies, I think they're working on the insurance companies to ban basements so they can build more storage facilities. But on to the real question, foundation walls that peak above grade, right? And then when you're starting the sill plate to go up and the whatever your cladding is, whatever that siding is, you always have the gap from the bottom of the siding to wherever, let's say you're using tar or dimple on that foundation wall. That gap in between is going to range from, let's say, 4 inches to 24 inches in height, if we're dealing with inches. And that's the only area that has the exposed concrete. And so water gets in through that and then has a more difficult way of getting back up. What are some recipes for dealing with that area? And I get it, the landscaping people don't want anything there. The cladding people and the architects don't know how to draw it, but forget everyone. What needs to be done?
Well, if you're doing exterior insulation, you're kind of cantilevering that out. Concrete face insulation board that you can embed a foot or so down into grade is a really good solution. And then if you're not doing exterior insulation, you're kind of all on the same exterior plane, and that would be kind of a goofy detail because it would bump out at the foundation. You could do like sheet metal, like a heavy gauge sheet metal flashing and take that down and have that shingle lap over top of your dimple mat and your waterproofing membrane, etc.
I like that solution. Why do you think it's evident that it's never addressed? Like, forgetting the fact that we seldom see enough exterior insulation. Why is that area always just left as exposed concrete? Is it just because we're not used to the practices of truly protecting our building from water?
Yeah. Cost?
Yeah.
Yeah, I've seen exposed dimple mat coming right out. I can't expect that to last more than 5 years or less than a decade anyways, right? It's not really a solution.
It's not UV stable, right? It's supposed to be covered.
Yeah, it'll get banged up and I mean, you don't even want your drainage mat to be coming up because then that's actually actively draining water from your surface. Your surface should be sloped away and kind of create that waterproof cap, whatever that is. And then your drainage mat is exposed or not exposed, but is thereafter underneath. So you're not putting extra stress on your weeping tile system, right? Like, why are you actively collecting water right?
Yep. I've asked this question for 15 years of my life to Peter Yost, and he always says it's the vein of my existence.
Yeah. And Mark, what you'd probably hate the most is when an architect specifies that it's board form. So now he wants to showcase that concrete in a beautiful detail, and all of us are being like, no, that is a thermal bridge. It is bringing water in. Like, no. So I could tell Peter just swinging his hat, the wingnut hat, just being like, when are we going to learn? When are we going to make, better details?
As Steven says, when Peter and I are arguing, he's always like, everything has the weakest part of a project, and that's usually it everywhere you go. Thanks, guys. This was brilliant.
Thanks, Mark. Thanks for joining us. And Grant, you know what? Maybe that's a good segue. We should wrap things up. We appreciate you sticking on for an extra 30 extra minutes. We got 90 minutes of Grant talking about vapor control layers and basements. And like we said, we could carry this conversation all night long. But I know Lori is pushing that button here. It's getting ready for bedtime for her, dinner time for me on the West Coast, and all you in between. I'm sure you got some other things to do. So Grant, appreciate your time, appreciate your insight. I actually take away the history lessons and the book recommendations to make sure my bookshelf has got full of those good books after I read them, of course. So, Justin, Lori, if you guys got any other comments, we'll let the big dog hit the ejection button, and we'll carry on with our evenings, days, depending on where you're at in this world. Any other comments?
No, I'm ready for bed.
All right.
I just wanted Connor messaged me. He got kicked off because of Wi-Fi. He just wanted me to thank you, Grant. It was an excellent presentation, and yeah, thank you very much.
Well, thanks you very much for having me. I'm happy to share my insights and thoughts and with the community and have these discussions. So be critiqued as well, right? Like my information, what I'm coming from is what my best understanding, right? To share. And if anybody can help, correct me in certain situations, I'm here to learn too.
Yeah, Grant, no, great insights, great information, and eloquently discussed. We appreciate your efforts. And again, now everyone who missed it, they're gonna have it on YouTube to dive into this detail. So it's fantastic. So Aaron, who unfortunately missed it, he will have to watch it on YouTube when we get it posted. But other than that, we'll say goodnight to you, Grant, and to everyone else. See you next month for BS&BEER Canada, where again we get to hang out with a bunch of Canadians, drinking beer, talking building science, and hanging out with some really good people. So, good night, everybody. Talk to you soon.
See you guys.
Bye.